Okay, so we're in 3.1 and we're going to do a couple of different problems. The directions are right here. It says for the problems, the recursive rule for a polynomial is given in the form of this: f of n equals f of n minus 1 plus rate of change. Now, if you're unfamiliar with recursive rules, no problem. Just kind of ease into them as seeing them. So the first thing that you should know about recursive rules is the way we say next is f of n. Okay, the way we say next is f of n. The way we say previous is f of n minus 1. And then your rate of change. Your rate of change is how fast it's growing, right? So plus 7 plus 7 plus 7, or plus 2 plus 5 plus 7, whatever the rate of change it's going. It's just this extra stuff on the end. So then they say, they gave you this, and then they want you to find the recursive rule to find the first 5 values, boom. Identify the rate of change, classify the polynomial, and then use the differences to check your answer. So I'm going to be doing these not in the order that they say, and I'm going to be checking my answer not in the order that they say. And let's see if this makes sense. So the first thing that I see is they gave me this thing right here. F of 1 equals -3, which you should know what that means. What does f of 1 equals -3? What does that actually mean? Oh no, my iPad says it's not working. What is f of 1 equals -3? What does that help us do in this table? Hint, hint. Where does it go? Yeah, this literally says when x is 1, y is -3. So a better way to write this would be, 1 comma -3. So Ms. Johnson, if that's what they mean, why don't they write it like that? Because this is function notation, and you'll see that it is actually very helpful, especially when we're talking about like transformations of a function, because that's what it is. Okay, so very good. So it's 1 comma -3. So where do I put that -3? Next to the 1. Exactly. Okay, so this says starting at -3, they want you to do something with this. So like we said earlier, this is next equals previous plus 2n. Plus 2n. So what? You want me to add 2n to it? Yeah. So one of the ways that you can fill out this chart is either by figuring out the rate of change and putting it here like I did to this one, or just by plugging the second number in. So I'm going to show you how I plug 2 in, because this is a different way of doing this one. So if you want to go find this video, it's very similar. So here it's f of n equals to f of n minus 1 plus 2n. So I'm going to plug 2 in for n. So I'm going to go f of 2 equals f of 2 minus 1 plus 2 times 2. Okay, wherever I saw n, I put a 2 instead. Does that make sense? So I went n2, 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 right? That's what I did, n2, n2, n2. And then I'm just going to simplify and solve. Okay, so then that becomes f of, hey, what's 2 minus 1? What's 2 minus 1? Oh yeah, that's 1. Plus, what's 2 times 2? It's 4. But Ms. Johnson, that doesn't look like a number. Hold on. What's f of 1? What's f of 1? Yeah, it's -3. You told me that up here, Ms. Johnson. Oh, okay. So you want me to put -3 there? Yes. Okay. So -3 plus 4. Oh, that's just 1, Ms. Johnson. Oh, yeah, very good. So you put a 1 there. So f of 2 equals 1. Does that make sense? Okay, can you do me a favor? Can you now plug in f of 3? My computer is going to catch up to you, I promise. This is the number 1 here because -3 plus 4 is 1. So there, f of 2 is 1. Can you now pause the video and figure out what f of 3 is, just so you can get used to plugging in here? So go ahead and do that. Okay, so hopefully you plugged in 3. I'm going to scoochie this over so you'll see 3. Give me 1 second. Okay, so I want to plug in and find f of 3. So again, I'm going to use that same equation. And then I'm just going to plug in. So f of 3 equals to f of 3 minus 1 plus 2 times 3. Okay. So this is equal to f of 2, which right now you should be like, wait, who's f of 2? And in like regular English, this just says, what is your y when x is 2? What is y when x is 2? Do you see how much shorter that is than to actually write all that out? So that's why function notation is helpful. F of 2. What's your y when x is 2? And so you're like, oh, Ms. Johnson, it's this guy right here. Exactly. So let's just put him right there right now. Right? He's 1. That's what f of 2 is. It's 1 right there. And then you're like, oh, Ms. Johnson, I know what 2 times 3 is. That's just 6. Exactly. So we're going to add 6 to that. So we get 7. So f of 3 is just 7. Okay. Ms. Johnson, do I have to do this for every single one? Not really. Because this says right here, next equals previous plus 2n. So that means if I want to find this guy, I'm going to take the previous, that's 7, and then add 2n to it. Yes. What's my n, Miss Johnson? Well, if you're trying to find 4's y, 4's your n. I'm going to say that again. If I'm going to try to find 4's y, or f of 4, this guy right here, I'm going to say that n is 4. So you want me to add 2 times 4 to it? Yes. So that's 8. You want me to add 7 plus 8? Yes. So that's 15? Exactly. So this is equal to previous plus 2 times 4. This is equal to previous plus 2 times 4. Previous is this guy right here, 7. Okay. My computer is a little bit slow right now. All right. So let me see if I can make it go a little faster here. Okay. So then there it goes. It's previous plus 2 times 4. So then that means, Miss Johnson, this guy, f of 5, would be previous plus 2 times 5. Yes. So that's 10. 2 times 5 is 10, Miss Johnson. So, and the previous is 15. So that's just 25. Exactly, 25. Very good. Okay, so we filled out our table, yay. Our rate of change, if you look at the structure right here, our rate of change is the guy that sits next to previous, right? So where is it? Where is our rate of change? So here's our function. Where is our rate of change? Yeah, it's the 2n. See, he's sitting in the same spot. Like if I could take this, copy and paste it and put it right on top. Do you see how you can play matching? F of n, f of n. F of n minus 1, f of n minus 1. 2n is in the rate of change spot. So they match. Very good. So this is just 2n. So it's this guy here. Right? So it's just 2n. And what type of polynomial is this? Now, in our conversation earlier, we talked about the rate of change. If the rate of change is linear, this is linear. How do you know it's linear, Ms. Johnson? Because if I graphed 2x, pretend that says an x, if I graph 2x, I should get out a line, which that makes it linear. If it's 2n, what is my polynomial type? What is my polynomial type? Yes, it's quadratic. Very good. So I'm going to write quadratic over here. Sorry, I'm squeezing everything in because I forgot that I have to actually write an answer here. I could scoot you over. Here, let me put you over here. Oh, let me put you over here. Over here. Sorry, we're confused on where to put you. Okay. So, oh, I forgot this little parenthesis. So does this make sense why it's quadratic? Because if this is to the first, then this is going to be to the second. Right? If this is to the first, then this is going to be to the second. Right? If this is a constant, no ends, then this is going to be linear. Right? And then it says, use your table of differences to check. Okay, so I move this really quick so I can check my differences. I don't know, maybe I'll do this like this or something. So then now I'm checking my differences. So here, this is 4. So here, this is 6. So here, this is 8. Here, this is 10. Because these numbers aren't the same, I know it's not linear. Okay, so no problem. Let me just try my next set of differences. 2, 2, 2. Okay, Ms. Johnson, they're all the same. What does this mean? Because these are all the same, then that must mean it's quadratic. So here, quadratic. Why is it quadratic? Why does this mean it's quadratic? Why is it quadratic? Very good. Okay, because the second set of differences, Ms. Johnson, what do you mean by second set? So my first set in this, like, I don't know, pinky reddy color, right? This guy, he was not the same. So I knew he was not linear. My second set, so technically the differences of the differences, right? The differences of the differences is quadratic. So since these were all the same, then it's quadratic. Ms. Johnson, is it quadratic because that's a 2 right there? No. It's quadratic because the second line of differences, first line, second line, are all the same. Ms. Johnson, if this was like an 8, would it still be quadratic? Yes, because it's all the same. 8, 8, 8, 8 means it's quadratic. Okay. Any questions on this? Okay, let's review. Ready? First step. Let's see. How did we get -3? Where did this -3 come from? Yes, they told you in the very beginning. Very good. Where did the 1 come from? Where did this 1 come from? Where did this 1 come from? Yes, we plugged in f of 2 to our function, and then we got it out. So when you plug in, it looks really funny because it says f of 2 minus 1. Well, 2 minus 1 is 1, and it's f of 1. But you just told me that f of 1 is -3, right? -3. So then that I simplified and it became 1. Good. Where did 7 come from? Yeah, now we plugged in f of 3. Now you can continue. You can plug in 4 and 5 and 6, or you can read this, and then that's how we did it down here. We said, oh, that means previous plus 2 times n. Now, if you're trying to figure out your fourth one, your n is 4, right? This all was right here. Okay. The rate of change, how did we know it was 2n? How did we know that rate of change was 2n? Yeah. Because of this structure that they gave us, right? They said f of n, f of n, f of n minus 1, f of n minus 1, plus rate of change, plus rate of change. So this guy hanging off the end there, he's your rate of change, Ms. Johnson? Yes, he's your rate of change. It looks funny for him to be a rate of change as 2n. This is kind of like the first time you're looking at it like that, but yeah, looks funny. Okay, how did you know that it was a quadratic polynomial? How did you know that it was a quadratic polynomial? Yay. Okay, two reasons. Number one, first set, not the same. Second set, the same. Quadratic, Miss Johnson. Very good. One way to tell that this was quadratic was that the second set of differences was the same, meaning it's quadratic. Versus here, see how this is your first set of differences, it's the same? That meant it was linear. The other way that you can tell that this is a quadratic is because if your rate of change is to the power of, do you guys all see that this isn't an invisible one? Here, I'll put it in my glittery pen to pretend that he's invisible. So do you see how n has an invisible power of 1 right there? Right? Because he has an invisible power of 1 there, your polynomial is going to be 1 degree higher than that. So it's n squared. So if your rate of change is linear, meaning to the first, then your type of polynomial will be to the second, which means it's quadratic. So there's a couple ways that you guys can tell. Okay. So now I'm going to make you do number 12, and I'm looking at number 12 and it's a little bit different. So I want you to take your time right here just to do number 12 to see if that makes sense to you. So go ahead and do number 12. And then we'll check back in a second. Okay, so you had a chance to do number 12. Okay, got it. So let's do number 12, and because now that you get it, I don't have to teach it. I'm just going to ask questions and you're going to help me fill stuff out. So first of all, what is the rate of change? Where do I find that? Yeah, it's at the end. It's this guy here. N squared. Oops, I'm still in my cute little glitter pen. Let's undo that. N squared plus 3. And because my rate of change is n squared plus 3, what is the type of polynomial I'll be looking at? Yes. Why would this thing be cubic? What tells you that it's cubic? Yes, because if this is n squared, then you add 1 to the power, then that would be n cubed, which would be to the third, right? Which was a cubic. Okay, then you plugging in, I'm pretty confident that you guys know how to plug in here. I'll just do 1 just so that you're comfortable with it. What goes right here? Yes, a 1 goes in here. And then you have options. Do you want to plug it in? Do you want to just plug it into the rate of change and then add that to your previous? You have options. Because I know that this is the rate of change, I'm going to plug in my 2 to my rate of change. So that's 2 squared. That's 4 plus 3 is 7. That's how much I'm adding to my previous. That's how much I'm going to add to the previous. So this is going to be 1 plus 7, which is 8. Okay. And then again, I'm going to keep doing that. So 3 squared would be 9 plus 3, which is 27. Wait, 9 plus 3, which is 12. Sorry. So this is going to be 12 plus 8. So this is 8 plus 12. Well, that's just 20. Right? And then if I continue on, the 4 squared is 16 plus 3. That's 19. So that's 20 plus 19. Well, that's 39. Last but not least, 5 squared is 25 plus 3 is 28. So that's 39 plus 28. So that's what? 40, 68, 67. So that's 67. So check my math. Whenever I do math in my head, I got to check it. So the way I did it was I pretended this was 40 and then I added it to 28. That's 68. But then I added much too much. So I took away 1. Okay, so that's 67. So I filled out my 5. I filled out my 5, I found my rate of change, and I checked the polynomial. The last little thing that they wanted you to do is check your sets of differences to do that. So I assume that when I do that, it would be a cubic. It would be the third row of differences. So I'm going to leave that to you all to make sure that you know how to do that. Again, biggest, what's the deal here, Miss Johnson? What's the biggest thing that you're supposed to know? Number one, when you're given a recursive function, don't be like, what does this say? Just remember, this guy is next. This means previous. And this is your rate of change. So that's where your rate of change is. Your rate of change is related to your type of polynomial because it's one more than that. And squared for your rate of change. Miss Johnson, what about this +3 business? I don't really care about him when I'm telling you about my type of polynomial because he's just like extra. So I just care about n squared, the highest power. So then that's n cubed. And then plugging in is just a matter of you really understanding and being able to work with this, okay? Okay, very good. Good job.